Problem number 2 says, use graphs and tables to identify the horizontal isotopes. So problem number 2 gives us the function f of x is equal to sine of 2x all over x. And so if we're going to graph this, because that's what it wants us to use, is use the graph to determine any horizontal isotope, which you could look at and see what it is, but I guess the challenge would be is like, how do you define that algebraically, I guess, right?
Divided by x, not 2.
Oh yeah, thanks. Alright, so now let's look at the graph. When do horizontal isotopes occur?
There's a like boundary.
Yeah, it's like a boundary. So
That'd be 2 and like negative 0.5.
So horizontal, but what I'm talking about specifically, and you'll notice this in your textbook, there's lots of reasons that we have horizontal isotopes. But what we're really focusing on are rational expressions, fractions, right? That's where horizontal isotopes occur, is at end behaviors. Okay? So horizontal isotopes, although they're not always completely isotopes, they're talking about end behavior. And end behavior is a fancy way of saying the limit as x approaches either positive or negative infinity of the function f of x. Okay, so there's a lot of clues here. If I zoom in, and I'm going to zoom in just a little bit, we'll do zoom trig. What we'll see here is that when x equals 0, that is our maximum value, but it's not defined. Well, that's a vertical isotope, and that's a different story. They could care less about the vertical isotope. But what is that approaching? Well, if I go a little bit to the left, it looks like it's approaching 2. If I go a little bit to the right, it looks like it's approaching 2. We might say that there is a, there's a horizontal isotope at 2, but there isn't.
What?
So we want to study the end behavior. That's what the textbook is really saying, is we want to study the end behavior. What does it look like it's doing? In other words, as I approach negative infinity in the x direction, what are my y values doing? Changing, but getting closer and closer to what number? 0. Right? And if I take the limit, well, if I go in the other direction towards positive infinity, and it'll take me a second to get there. Now, normally when we graph this sort of thing, we think of a horizontal isotope as something that the y value can never be, right? And that's technically what a horizontal isotope is. But the way the book described it was end behavior. So now as I approach positive infinity, if I were to keep going this way, what do you notice about the y values? What's it approaching? 0.
Does it ever actually get to 0 or no?
Well, here's what the answer in the back of the book says. It says that the limit as x approaches infinity of f of x is 0, and the limit as x approaches negative infinity of f of x is equal to 0. Now that's what we just showed. Now a horizontal isotope might occur at y equals 0. But how do I show that? Well, that would mean that the y value cannot equal 0 at all. So do you see the y value equaling 0 at all?
No.
See, in order for the y value, so we got to study sine of 2 theta. Okay? That's what we got to study. What happens in order for this? In other words, if I were to say y cannot equal 0, that means that f of x cannot equal 0, which means that sine of 2x, sine of 2x cannot equal 0, because that's what defines 0, right? Let me show what I wrote down there. In order for this thing to equal 0, I've got to have a 0 in the top and something on the bottom. Now the only restriction on the domain is that x cannot equal 0. Well, is there a possibility that y might not equal 0? I don't know. Well, it would occur when sine of 2x equals 0. Now we know sine of x equals 0, but is there some sort of change when we do sine of 2x? How does that change things? So one way we could do that is we could just look at the function sine of 2x. So if I come in here and I graph this, oh, that's interesting. Let's go back and zoom. Can sine of 2x equals 0? Now remember, the 2x part just changes the period in which the function, it just shrinks the function down. So normally sine has a period of 2 pi, but when I put that 2 in the front, what is my period now going to be? 2 pi divided by 2, which is just pi. So I should have a 0 at pi over 2. So what I should be able to do is if I hit trace and I enter in pi over 2. Now think about that before I plug it in. We know that according to the unit circle x, y, if I have a unit circle, and this is cosine comma sine, when does sine equal 0? At 1, 0, that occurs at an angle of 0, and then over here at negative 1, comma 0. And that occurs at pi. If I take pi over 2 and plug it into this equation, I'm saying 2 times pi over 2, which is really just pi. Are you guys with me on that? Does that make sense? So if I enter this in, my y value should equal 0, and it does, and then the whole thing would equal 0. Does that make sense? So if you looked in the back of the book says y cannot equal 0, but really there is no asymptote in the way that we think in terms of asymptote. There's a behavior, and that's based on the limit. So I don't really agree with the way the book defined a horizontal asymptote. It only applies to specific cases. What we're really interested in is in behavior. So if you had this written down, I'm okay with that. If you tried to find a horizontal asymptote, you can't. And so basically, if I come back here and I say divided by x, and I find the graph, if I plug in trace and I plug in pi divided by 2, guess what my y value is? 0. So to say that we have a horizontal asymptote at y equals 0, or to say that y does not equal 0, which is what my book says, is wrong, because clearly y can equal 0. So it's not an asymptote in the sense that you guys have been taught. But if we look at the end behavior, it does approach 0 both as we go towards negative infinity and positive infinity. Does that make sense? So I can see where there's some confusion on that.